Good morning, class, and welcome to today's lecture. So, today we're going to be looking at data structure and algorithms. So, before we look at the lesson for today, we're going to be looking at the scheme we will cover for this semester. So, the first one we'll look at today is Introduction to Data Structure and Algorithms. So, the second topic will be the algorithm and time complexity, where we'll look at the some of the asymptotic notations like the big O notations, the big theta, and the big omega. But we'll focus mainly on the although we'll focus on the tree because the big O notation mainly is focus more on the worst case scenario. So we'll focus more on the three, where we shall look at the types of time complexities where it will cover the type of time complexities. The examples we'll look at will cover both time and space complexity, where we'll look at the constant time complexity, the logarithm time complexity, the linearitic time complexity, the exponential time complexity, the quadratic time complexity, then the other time complexity, or the log. Okay, I've mentioned the logarithm time complexity. The other type, like the cubic time complexity, the factorial time complexity, but we will not actually go deeper into that, but we'll look at more of the common time complexities in the structure and algorithms. So the other topics we'll look at here is recursion and backtracking. We'll look at some examples of algorithms that has to do with recursion and backtracking, like the backtracking, which mainly graphs, the binary search trees, the n-queen problems, and just some few algorithms which are picked to demonstrate how recursion and backtracking works. So we'll look at a graph, right? So we're not going to look at the graph, we'll look at directed and undirected graph, and then some examples of graph like the Dijkstra algorithm, the depth first search, breadth first search, the Kruskal algorithm. So we're going to look at some of the algorithms, some graphs, right? So we'll look at the hash tables and we'll look at trees. So these are the topics we shall cover in this semester. So lesson one is introduction to data structure and algorithm. So we need to understand what is data structure and we need to understand the algorithm. So while learning data structure and algorithm, so as a computing student, it's very necessary and very important to understand how to understand data structure and to understand how to write algorithms. Although we shall not basically use any programming language to demonstrate this, but we shall use a formal way of writing the pseudocode, which is close to the programming language, right? So we shall explain some common terms of how this works. So now that structure, although before we go into the lesson, we need to understand the objective we should cover in this lesson. So the first one here is to understand what data structure and algorithms are, and to learn why they are important in computing, and to explore basic data types of data structure and algorithms, right? So now data structure is a way of organizing, storing, and managing data so it can be accessed and modified efficiently. So by default, we know that computer is dummy, right? But computer is designed to process information, to process and retrieve information very fast, right? But how can computer? But we as a developer, we need to we need to give computer that instruction in order for for computer to perform that particular task, right? So that is where this algorithm comes into play, and that is where data structure comes into play because we need to know how to organize data so that computer can be able to understand this in order for files for data to be accessed and modified efficiently. Right? So that's where we come in, and that is why we're learning this course. Okay. So we'll look some at some basic data structures and algorithms, right? Basic data structure and algorithms. So the first one here is the array, or the array, which is a collection of items identified by index or keys. So in this array here, in this particular lecture, as we move on, I'll call this a list because we basically work with lists, right? So you can see that identified by index or keys. Like when I say keys, like, let's use an example. Let's use dictionary for example. So dictionary is all about the collection of key value pairs, right? So now Let's assume that in our algorithm is denoted, the list is denoted as a square bracket like this. So we have a collection of items, and the collection of items are of the integer data type, which I will explain what data type is to you as we move on in the course of this lecture. So let's assume that we have 2 as an item, we have 4 as an item, we have 6 as an item. So you can see now these are the collection of elements, or we can call them items, which is identified by indexes. Now, each of these items, right, are located in a particular index, and in the computer, right, the first one is located, it starts from located in index 0, and this is located in index 1, and this is located in index 2, right? So that is how it works. So if we have another element 5, this 5 is located in index 3. So that is how this works, right? So now linked list. Now linked list is a trace of connected nodes where each node contains data and reference to the next node. So this one is like a list of lists. Like we have a list like this, right? And we have a pointer linking to another list. And we also have a pointer linking to another list. So which may be single, maybe double, or maybe circular, right? So then we have the next one is a stack. So a stack is a collection of elements that follows the last in, first out principle. The last in, first out principle. Right? So we shall learn how this works as we move on in the course of this lecture. Because when I mean last in, first out is, for instance, you can see that in this, let's assume here that 5 is the, let's assume here that 2, let's assume here that 2 is the last items which is being inserted into this list, right? So it means that 2, if we are popping out any items from here, the first that will go out here is 2. So that is what this stack means. So it has to do with the collection of elements that follows the last in, first out principle, while the queue is the first in, first out principle. The first in, first out. So let's assume that 5 is the one that is the first in this element. So 5 will be the one going out because the first in, first out principle. That is how the queues works. So we shall learn the another example of that structure is the trees, which is an hierarchical data structure with a root and branches, which is part of what we will learn here, where we'll learn the binary search, the binary search tree, where we'll learn that. We'll learn that. So we'll learn the transversals, how the in order, transversal, post order, pre order, the level order. We shall learn that how this works. Then the graphs, we shall learn how the graph work, which is a set of nodes connected by edges. Then the hash tables, a data structure that map keys to values for efficient data retrieval. We shall also learn that because it's part of the topic we'll learn here in the scheme of data structure and algorithm. So now we have understood some basic examples of the data structure. So we need to understand what algorithm is. So an algorithm is a step-by-step procedure or formula for solving a problem. It's a step-by-step procedure or formula for solving a problem. It is a sequence of instructions that takes inputs, process it, and produce output. Right? So it's an instruction you give to the computer that takes the input and process it and produce outputs. And that is the core scope of this course. And that's what we're going to be doing here. Where we're looking at um, certain algorithm where this falls under the complexity, which we'll look at in our next videos in lesson 2. But lesson 2 is divided into a down to other um, sub lectures. So the same thing applies to search algorithm, the linear, which this one also falls in this binary search, and linear search also falls in the linear time complexity and this logarithm time complexity. And we'll look at the graph algorithms also, then the dynamic programming, the divide and conquer, all this we'll look at. These few nerves, all this we're going to be looking at them, which them falls under each of their time complexities. Well, we'll learn them very well, but this is just an introduction class. So these are some examples of algorithm. So it's not basically when we say algorithm, remember it's a step-by-step procedure or formula for solving a particular problem. So it doesn't really mean that all these are the basic examples. Now you can think of your own algorithm to solve a problem. Let's assume that on your way coming to school, right? Definitely there are some steps you need to take to come to the school. So the steps you take to come to the school, you have solved that problem of coming to the school from home to school. So that's an algorithm. Because look at the definition, an algorithm is a step-by-step procedure formula for solving a particular problem. You have solved that problem. But in computing here, where we're going to be writing that problem in order for computer to process that task based on what you have written, right? Remember, computer is dummy. If you give computer a wrong algorithm, it will perform wrong computation. But if you give computer a good algorithm, it will perform a very good computation. And during the process of this course, we're going to be learning how to optimize an unoptimized algorithm in order for the computer to process that um algorithm very fast and efficient. So we're going to be learning that, right? So now, why are data structure and algorithm important? Now, the first one here is efficient problem solving. Efficient problem solving. So, proper use of data structures and algorithms improves the efficiency of solving complex problems. Now, optimization. So, they help in optimizing time and space complexity, right? Time and space complexity. We'll learn that in the next lesson 2 video. So, scalability. Efficient algorithm. Remember, like I said, efficient, which we are going to be learning how to solve, how to write good algorithm, and how to think about a good way to write an algorithm for computer to process the algorithm very fast and scalable. So efficient algorithm and data structure ensure that applications can scale to handle large amount of data. But remember that despite that structure aids for scalability. Now, but if you write an algorithm in a wrong way, right? So this will defeat this important. It will defeat this, so it makes it like a disadvantage, right? I'll give an example. Now let's assume that you're writing an algorithm to retrieve a 10 million record. Let's assume that there's a 10 million record stored in the computer and you want to retrieve it to the user. Now, if you fail to write a proper algorithm to retrieve that 10 million record, that it will become very, very slow. But if you understand the algorithm work and you write a proper algorithm to retrieve that 10 million record from the computer to the user, then it becomes fast. So this determines how you write the algorithm to be scalable and efficient, right? So, like I said, efficient algorithm and data structure ensures that applications can scale to handle large amounts of data. That's why we use the word efficient, right? That's how we use the word efficient. So now, interview preparation. So many coding interviews, right? So based on my experience in software development, so most of the interviews I've went to are their questions mainly concerns data structure because the companies believe that if you can be able to understand data structure and write good algorithms, right, on how to solve a particular problem, they believe that you are a better developer. So the foundation of software development, so from building databases to designing operating systems, they form the core of software development. So that is the reason we're learning this course. So to get started, there's one thing we need to understand here, which is the data type. So is a type a data type is a classification that specifies the kind of data a variable or object can hold in a programming language. Now, there are some basic primitive data type that almost all programming languages have, which are the integer data type, which is also referred to as a whole number. Let me remove this void. Let me use this. So we have the integer data type, which we also call the basic data type provided by most programming languages. So we have the whole numbers, which is 1, 45, minus 5, minus 4, and so on. So these are the integer data type. So the next thing we have here, next primitive data type we have is a floating data type. So the floating data type is the decimal numbers like the 3.14, the 1.4, 0.4, 1.14, and so on and so forth. So these falls under the floating data type. So we have the string data type, or we can call it the scatter data type, right? So which take alphanumeric values, right? So we have the Boolean data types, which represented as the true or false values. So these are the mainly basically the four primitive data types. So we also have the non-primitive data types, which are the abstract data type, which is also called the high level data structure defined by their behavior, which we have explained this, the list, which has to do with the collection of items. We have the stack, we have the queue, we have the set collection of unique elements or distinct elements, right? So we have understood what data type is, right? So we're going to be working with the primitive data type, and also one of the common non-primitive data type we also will be working with more here in this data structure algorithm is the list, which is a ordered collection of items here. So we're going to be looking at what variable is, because we'll be working a variable when we'll define writing our algorithms, right? So now what is a variable? A variable is a name storage location in a computer program that holds a value. So let's assume a variable can be X, right? So a variable can be a variable can be B, a variable can be John, a variable can be Peter, right? A variable can be any name, but you shouldn't write a variable like this, space this, right? Doesn't make sense. So just a single word. Or even if you want to write double word, you use another score than this, right? So a variable is a name storage location in a computer program that holds a value. So the value of a variable can change during the program execution, right? Can change during program execution. So variables are used to store data that your program manipulates, right? Data that a program manipulates. So now, in some programming language, we can have a variable like this, right? We can have a variable like this. So now this variable can hold an integer data type of 4, right? So in also some programming language, we have something like this, int x equal to 4. So this is an explicit way, like this is an explicit way of defining a variable. So this is an implicit way of defining a variable, right? So now when this variable x, sorry, this x, let me use small letter. So this variable x is holding 4, right? It means that uh, the computer understands that the variable x is an integer, right? But in some situations, the computer will not understand it except you explicitly defined the int, right? The int like this in some programming language, right? So programming language like Python is implicit in nature like this, right? It also explicit in nature in some ways when we define functions, but by default it's implicit in nature like this. Okay, so that is how the variable works. So we've understood variable. You can see that variable holds a value. It's a name storage location in a computer that can hold a value. You can see. So this variable can also hold a string like John, right? Can also hold a boolean like true. Can also hold where we float like 3.14 and so on and so forth, right? So that is how it works, right? So that's why we're using a variable as a name storage location in a computer program, right? Because it holds value. So like I said, the value of a variable can change during the program execution. And so that is how it works. So now, how to write a formal algorithm, right? How to write a formal algorithm. We have the formal and informal way. The informal way is just like a natural language processing way, just like the way we talk. That's how the informal way works. So now, mainly look at how the more of the formal way. So now this approach uses structured, precise, and universally understood notations, often resembling mathematical or programming language. So it's idea for professional documentation, technical discussion, or implementation in software. So characteristics. So the first one is structured, which is steps are numbered or formatted systematically. So the second is detailed. It specifies input, output, and every action clearly. Then the third is standardized, may use pseudocode or specific syntax. So we'll be using more of pseudocodes, right? So more of pseudocodes. Now let's show an example. Say assuming that we're trying to find maximum of two numbers. Now, the first thing we need to do here is to input A and B. So A and B are variables, right? A and B are the variables. So this A we hold a number and this B we hold a number. And a number is an integer data type, right? So now if A is greater than B, then this mass, let's assume, okay, let's do something. Let's assume that A holds a number, A holds a number of 4 and B holds a number of 6. So it means that A, remember here is holding a number of 4, which A is a variable, and B is holding a number of 6, right? So now we are passing this instruction to the computer because the aim of this algorithm is to try to find the maximum between A or B, right? And now this mass is also a variable, right? So this mass is just to keep the maximum number. So if A is greater than B, hmm, then assign the number in A to mass, right? So look at it. So if A is 4 and B is 6, right? So is A greater than B? No, right? But because B is greater than A, else we will now assign B to the mass. So at the end, the mass will give us what? 6, which is B. Is outputting 6, output mass, then end. So this is just a common way of writing. It's a common formal way of writing a simple algorithm. Right? You can see how to do that. It's just a common way of writing an algorithm. So you can see how to write a formal algorithm. So this approach uses plain. So everyday language, like the common languages we use now, describe the step. Is suitable for brainstorming, explain to a non-technical audience. Okay, sorry, we are in the informal algorithm, sorry. So informal way, this approach uses plain, everyday language to describe the steps. So it is suitable for brainstorming, explaining to non-technical audience, or quickly jotting down ideas. So this algorithm is mainly important for people that's actually not in the computing field, right? But this one, when a computing professional says this, he understands it very well. But you guys are computing professionals, so but this one is very easy, like characteristic. Simple language is just natural language without technical jargons, right? Without all these technical things, because we'll be seeing more of these technical things when we're looking at some of advanced algorithms, right? Which make it more difficult to read by non-professionals. But in a formal way, in informal way, you're just writing it straight up the way it works, right? Like in English terms. So flexible, focus on conveying the logic rather than strict formatting. So readable, easy for beginners or not technical people to understand, right? So now, this is an example of an informal way of that algorithm. So, like this, we are finding the maximum of two numbers. So, algorithm in informal ways. Okay, you're starting the process. You take two numbers, A and B, right? Remember, these are variables that holds the two numbers. So, you check which number is bigger. So, if A is bigger, then it is the largest. Otherwise, B is the largest. Display the largest number. Then finish. You just like you're writing. You can see the steps. You're trying to compare A and B. There's a number, there's a number, and this variable holds that number, and you're trying to compare them. You're trying to check which one is bigger, and then you are outputting the bigger one. So that is how the informal way works. It's very, very simple, right? So now examples of real world applications, right? So we have the social media platforms. Now, graphs are used to represent user connections, right? So let's give an example. For example, we have the Facebook, right? So in the Facebook, if you have a friend, now a friend of a if you have a friend that has friends, so those friends becomes your mutual friends. Now, how this works, how that application works is the use of graph, right? Is the use of graph. So we're going to be learning this, especially we're going to be learning how it works, how breadth first search work, how breadth first search work, how when you let's assume that they are connected nodes, right? So you are like you have a neighbor and your neighbor has two neighbors, right? So because those neighbors have two neighbors, then those neighbors becomes your mutual friends. So that is just the idea of how social media platforms are implemented, and this graph algorithm, this graph technique was used to implement the social media platforms like the Facebook, your TikTok, your LinkedIn, and so many other platforms that you know, like the friends and followers. So we have the search engine. So search engine, one the common algorithms used for search engine is the trees, especially binary search tree, and the hash tables are used for indexing. So that is how the search engine works. So you can see why we're learning this data structure and algorithm, right? You can see where they're applied. So navigation systems, so are going like Dijkstra algorithm, which we will learn, are used to find the shortest path between locations, right? So when if you are designing navigation system, then just know that Dijkstra algorithm is one of the common algorithms used for navigation system. We have the e-commerce system. So e-commerce system mainly uses the queues and stacks are used in order processing and inventory management. So databases mainly use hash tables and trees are used for indexing, especially relational database management system used for indexing and querying data efficiently. So in the lesson 2 video, we shall look at more of the core concept of this course, right? So this was the introduction and this is the assessment question. So I urge you guys to understand the assessment question so to prepare you for your exam. So thank you and God bless you. So we are done with lesson 1. So lesson 2, we're going to be looking at algorithm and time complexity.